What's good, everyone? So, today we're going to be talking about periodic trends, more specifically, atomic radius, ionization energy, and electronegativity. So, first one we're going to be talking about is atomic radius. So, atomic radius is just the distance between the nucleus of the atom and its valence shell, the outermost electron shell. So, what do you think the trend is down a group? So, a group is just a vertical column in the periodic table. So, for example, hydrogen, group 1 is hydrogen, lithium, sodium, potassium. What do you think the trend is? Do you think atomic size gets bigger or smaller? I'll give you a moment. Well, since down a group, we're adding more shells. So hydrogen has one shell, lithium has two shells, and so on. Well, the distance from the nucleus to the outermost shell must increase because we're adding more shells. Now, what about across a period, left to right? A period is just a horizontal row in the periodic table. Well, let me ask you guys a question. Do you think a valence electron from, let's say, Na is feeling the same pull from the protons in Na than, let's say, a core electron of Na? No, because the valence electron is further away. So, how do we calculate the actual force that the valence electron is experienced, the force of attraction? How do you calculate that? Well, all we got to do is take the atomic number, okay, which in this case is 11 for Na, and we subtract it by the amount of core electrons it has, which is 10. So that means we end up getting 1. And that means that the pull from the valence electron, it feels a force of attraction of 1 proton. Now, what do you think will be the Zeph of magnesium? Well, magnesium, its atomic number is 12, and it also has 10 core electrons. You see here, across a period, the amount of valence electron increases, but the amount of core electron stays the same. So it's basically the same thing as Na, except we added 1 proton. So 12 minus 10 is 2. Wait, that means the valence electron is feeling a force of attraction of 2 protons. Now, when magnesium feels a force of 2 protons, it's going to get pulled in more. The atomic size is going to decrease because the force of attraction is stronger. So, magnesium is going to pull the valence electron in more. Now, we're going to be talking about ionization energy. Ionization energy is just the amount of energy it takes to remove an electron from the atom in the outermost shell. So, what do you think the trend is for ionization energy? Well, we could use our information we learned from atomic size to answer this question. Because atoms get bigger down a group, it would make sense that it would be easier to remove an electron because it's further away from the nucleus. Therefore, ionization energy decreases down a group. It would take less energy to remove an electron from the valence shell. Now, across a period, we know that the Zeph, the effective nuclear charge, it gets bigger. And because the effective nuclear charge is bigger, it would take more energy to remove an electron through a period because the attraction is stronger. Now let's learn about electronegativity. So electronegativity is just how good an atom is at attracting an electron. And electronegativity follows the same trend as ionization energy. So down a group, electronegativity decreases because the atoms are getting bigger, so it's not that good at attracting electrons. And across a group, across a period, it would increase because, first of all, we know that atoms, they want 8 electrons in their valence shell. They want this full valence shell. So elements to the right want electrons more than elements to the left. Elements to the left, in fact, they want to lose their electrons. They want to give away their electrons. And another reason why electronegativity increases across a period is because the atoms, they get smaller, which means the attraction, it's going to be more attractive to the electron. The protons are going to attract the electron more. Now, one thing to note is that the noble gases, so the last group, helium, neon, argon, krypton, those elements don't really have an electronegativity because they have a full valence shell, which makes them really stable. They don't want to give away electrons. They don't want electrons. They're perfect the way they are. They're fine the way they are. They're happy. So they don't really get assigned an electronegativity value. And that's it, everyone. Hope y'all enjoyed the video and see y'all next time. Bye.